and you get ready.
Yeah, I'm ready. So shall I proceed?
Yes, sir.
Yeah, one sec. Hello. Yeah. Hi, everyone. This is Sudipto Shaha. I am from Regional Science Center, Bhubaneswar, and I will initiate today's valedictory session of Let's Do Science Festival 2022. So am I audible? Hello?
Yes, sir. Audible.
Yeah, thank you. So first of all, I will introduce myself because I am a curator here, and I am present here as because our project coordinator, Sir Sri Shaumen Ghosh, is on some other duty. On behalf of him and on behalf of Regional Science Center Bhubaneswar, I welcome you all to this program. So we have started this program on February the 28th, which is the National Science Day we celebrate in India. And we are doing this. We are doing this festival in association with different similar-minded organizations like Australian Consul General, Kolkata, Tata Institute of Fundamental Research, Odisha Vigyan Academy, School of Mass Education, Government of Odisha, and BCKIC, Bhubaneswar. So I thank all the participatory institutions for bringing this program into a success. Alongside, I would like to take the name of Sri Manish Kumar, a National Awarded teacher from UP, and Dr. Arnab Bhattacharya, Coordinator Science Popularization Wing, TFIR, and obviously Dr. Stuart Collagen, the famous science nomad. How can I forget him? It's my privilege to talk with you, Stuart, and I wish you good luck for your future programs also. So now I will just hand over the control of this program to Dr. Stuart, and I will request him to share his experience during this 5-day program. Dr. Stuart?
Yes, thank you so much.
Okay.
So it's always wonderful to be invited to come and join with the educators in India, and always a pleasure to work with such strong partners as we have in the National Council of Science Museums and the regional science centres, such as the one which is hosting and coordinating this event. My participation with this program is made possible because of the support from the Australian High Commission, and in particular the Consul General in Kolkata. Over the last several years, 5, 6, 7 years, COVID allowing, I've been a frequent visitor to work in India, both with the science centres, with specialist schools across India, face to face, and now with COVID, doing a lot of work via online and Zoom. It's a great honour to be invited, and it's also a wonderful opportunity to confirm the strong kind of Australia-India links that exist, particularly in the area of education. So across the week, tonight included, I will have run sort of 3 different sessions with educators. Some where the content was focusing on physics, some where the content has been focusing on chemistry, and tonight our session will be operating kind of under the umbrella of computational thinking. One of the reasons I'm always keen to work with Indian educators and Indian students is it's without doubt they all recognize the supreme value of a quality education, that the pathway to bettering themselves, bettering their families, their communities and the nation very much rests on education. So a great value is placed on education and wanting to find ways to improve it. And so within that environment, I am very grateful to be able to return to India, particularly during the National Science Week, and contribute and share some of the approaches that I have with my version of supporting education. So hopefully tonight will be similarly interactive as the sessions were earlier in the week. I'm not really here to give a lecture. I really do not like just lecturing or talking. I very much prefer to be doing things and interacting with my my audience, with my participants. So tonight, this is a very safe place. I'll be asking lots of questions. I don't want you to hesitate. I want you to contribute your thoughts, because I'm not interested in the correct answers, whatever the topic, physics, chemistry, computational thinking. I'm not interested in whether you know the right answer. I'm interested in how you think. And this is something which hopefully will come through in tonight's workshop. This, for me, a focus on how do we get people thinking, not just listening and trying to remember, but how do we foster what I call 21st century skills? So how do we get people to be critical thinkers? How do we get people to have the persistence to be problem solvers and the flexibility and to give them these tools, which once they graduate and they encounter problems that you haven't given them the instructions on how to solve, how do they go about working on those problems? So tonight is very short, but hopefully it's a start, and I will give you some ideas about how you might integrate some of these activities into your teaching, whether you're all maths teachers or general science teachers. We can do a lot to foster thinking, whether it's computational thinking or not. And so I hope you will join with me in that spirit tonight. And if you've got a response, an idea to one of my questions, please just hop into the chat window and put your ideas into the chat window. And myself and the staff at the Science Centre will keep an eye on the chat window. And if it's easier, we might get you just to talk to us about your thoughts and interact that way. So welcome. And hopefully you get as much joy from this evening as I will. So thank you very much. Would you like us to start the workshop now?
Yeah, just a minute. I will control the mic to Mr. Satpathy. He will introduce you once again and today's topic, then he will start.
Okay.
Okay. Satpathy Babu.
I start now, no problem.
Okay, thank you.
It is my privilege, to get in contact with Dr. Stewart. long time back in Kolkata. I remember that day when we all different participants from all of our centers congregated at Birla Museum in Kolkata. And then we started discussing various topics in science inspired by Dr. Stewart. And from that day, we became good friends. And we enjoyed his every action and every inspiration he is providing to all of us. And our participants also in this National Science Week Festival session also appreciated Dr. Stewart as we have taken the feedback, and they are very happy, sir, to listen to you this evening. And computational thinking, in India, we know many college students, engineering students, they after completing their engineering graduation, they are switching to software branch and getting engagement all over the world, especially in Australia, in US, in Europe, in Singapore, in Japan, in Korea. So we know that our children are good at software, but to be very frank with all of you, designing software and getting children acquainted with computational thinking, they are two different things. And getting acquainted children with computational thinking is the actually is the challenge of the day. Because if we orient our students in such a manner that their thought process is always logic based, and then only whatever study they do in future, in science, in mathematics, in literature, they will be logical in their approach, and they do not fail in any milestone they create. So in this context, I would request Dr. Stewart to introduce the session first regarding the objective of the session, and then plan accordingly and switch over to different designs you plan to implement today. So on behalf of all the participants, I congratulate you once again. And we are waiting for your session now. Thank you, sir.
Thank you so much. So let's make use of the time we have tonight. The topic that we're going to focus on tonight is we've selected is computational thinking. It's a topic that is being discussed and discussed with the schools. The various state education systems are looking to get some aspects of computational thinking integrated and delivered through the schools. And it's a new topic. It's a topic that needs to be supported, can only be supported through a reasonably different way of teaching. If I can give you an example of how different the goal is for doing computational thinking. For example, if I was teaching traditionally, I might give you a computer. I might put Microsoft Word on there. I might teach you to touch type. I might get you familiar with how to use all the menus on Microsoft Word. But once I've done all of that, have I made you a great author? You can touch type. You know where all the menu controls in Microsoft Word are. You can format it beautifully. Can you write me a great novel? And I hope you see the difference between those two goals. if I teach you how to use Microsoft Word and all the menus, maybe all I've done is train you to be a very efficient secretary. It doesn't give you the skills to have great ideas or to find important topics to write about. These are all very different skills. And our school systems across the world, this is not just India, our school systems across the world have evolved and be rewarded for kind of training you how to touch type and how to use the menus in Microsoft Word. We haven't really given space in the teaching to how to get people to have big ideas, great ideas, to be creative, innovative, or to solve problems, new problems. And that's one of the goals of computational thinking. And so tonight, I will share with you some of the activities, hopefully some fairly simple activities, to get you to see both how simple it is to bring students, yourselves, and learners into thinking about how they think, and to give some examples of some different ways of thinking that we will often encounter when we're exploring the topic of computational thinking. So tonight, I'll need you to do some thinking. And you don't have to get the answers, but you do need to try. And I want to hear how you're thinking about it. And that will give me the material to work with, is your thoughts. This, I promise, will be the only PowerPoint slide for the entire evening. When school systems are talking about computational thinking, they will often kind of present kind of four aspects, through four stages or four components of what is being accepted as being computational thinking, at least as far as the schools are concerned. And if we look on the left of this, that's sort of the more important side for the moment. The four aspects of computational thinking, the four skills, if you like, is decomposition, where if I give you a new or complex problem, you're able to break it down. So if the problem appears confusing, or your thoughts about how to tackle the problem aren't clear, that there is great value in breaking the problem down so that we kind of understand the nature of the problem. The kinds of problems which computational thinking is preparing students for might be what we call ill-formed questions, or unkind questions. They're questions where the question doesn't tell you what kind of a problem it is. You've got to work out what kind of a problem it is before you even start. Pattern recognition is one of the things which we will often bring to bear when we're trying to do problem solving, is to try and understand the problem, looking for patterns. Are things progressing in a particular sequence? Are there patterns? Are there regularities in the data? And that can give us clues about how the system is working and how we might work with it. Algorithms is really the part of this which I guess is closest to software writing. Algorithms is really just a set of rules that you can follow to solve the problem. So if you've got a very clear understanding of the problem and how to solve it, then you should be able to write down the steps involved for you or for anyone else or a computer to solve. But a computer can't solve a problem, even today, a computer can't solve a problem unless you define what the problem is and the sequence of steps that need to be done to solve it. And so algorithms is really just a word we use to describe that process. What's the algorithm that I need to go and get dressed and get to work? What's the series of steps that I have to do? Abstraction is one of the very valuable skills in computational thinking. You might be working on a problem that is at a brick factory. You may have a problem in sequencing how the materials arrive and how they're sorted and distributed and packed and laid out. But if that's your job, the skills that you're developing, the algorithms that you're developing to work efficiently that way, really don't relate to the bricks. That could be a system that applies to a textile factory or to an architectural firm or a great range of different topics. And abstraction is one of those things which is worth fostering with your students to get them to see the principles above the problem that's in front of them, because that will help them in two ways. They may be able to take the solution to the problem that they're working with today and apply it somewhere else. And the reverse can happen. They might recognize that this is a sorting problem. This is a problem in efficient sorting. And then they might go, all right, I don't have to worry about bricks. I need to find a good sorting algorithm. And they would go and look for that and bring those solutions in. But this is a way of thinking abstractly, not about the objects that are part of the problem, but about the system and the steps and the logic of the process that we're working with. So I think for me, it's important to think about those four categories. Sometimes you will see them drawn as kind of A, then B, then C, then D, and that you go around the circle in a particular sequence. In the real world, that's not true. Depends on the problem and the person working on it as to which one of those four skills may be the more important one on the day. And so what we'll do now, without spending any more time, is I want to involve you in actually doing some activities and thinking, and we're going to work through some strategies for solving problems. So to do that, which activity I think we'll do first is one which is familiar to my good friends there at the Science Centre. Hopefully they still remember some of these questions. Before I go to the workbench, I can see in my Zoom meeting bar that we've got 26 participants at the moment. We have 26 participants. And because this is a diplomatic connection between Australia and India, we should all be friends. I think we are. So imagine now that we weren't on Zoom, but that we were physically together, all 26 of us. And I wanted to make sure everyone shook hands with everyone else. So we have 26 people in our group, and I want everyone to shake hands with everyone else just once. So quickly, what's your thought as to the number of handshakes we need for every one of the 26 people to have shaken hands once and only once with everyone else in the group? What's your thought about what that number is, or what the process you would go through to come up with that number? How would you work that out? Don't worry about getting the number right. If you've got a process that you would go through in your head and you just want to put that into the chat window, just pop your strategy into that. So 26 people shake each other's hands once. How many handshakes are there? How many handshakes? I'll give you a little bit of time. Come up to 25. 25 is one offer. Do we have anyone with more than 25? Less than 25? What thoughts might you have? So 26 people in the room, they all have to shake each other's hands once. How many handshakes are needed? Have a think about it. You don't have to give me the right answer. You might just tell me how you would think about it. So you don't have to do the arithmetic. I'm not very good at arithmetic myself. 25 factorial. 25 factorial is a very large number. Let me see if my calculator can handle 25 factorial. Does my calculator here even do factorial? It's a very large number. Any other options? But thanks for your thought. And whenever I see the suggestions, when I see your answer or your strategy, it tells me how you are thinking about the problem. And I cannot emphasize enough how important it is, not only for you as the educator, but for your students to become aware of how they think about the problems and to verbalize it, to make explicit, to share how they are thinking about the problem. Because if you get the answer right, I don't know if you're smart or lucky, or if you get the answer wrong, I don't know if you're not very clever or you misunderstood the question. So the answer by itself does not give me very much information. Now we've got 26 very intelligent people here. I've only got two suggested or answers from 2 people. I'd like a few more. And as I said, this is a safe place. It sounds like a simple question until you try to work out the number. So we've got 25 or 26 times 25 or 25 factorial. Any other numbers? Is everyone shy or worried? So the workshop tonight really will need you to contribute your thoughts. It's no exam on the end of it, but I need to hear from you as to what your thoughts are. So Debbie has suggested 25 times 20, 26 times 25 divided by 2. All right. And so that's telling me a lot about how they are thinking about the problem. Okay. So when they go 25 by 26 divided by 2, they're going 26 people. Each person is going to have to shake hands with 25 people. And there are 26 of those. So there's 26 by 25. But if I shake hands with you or you shake hands with me, it means the same thing. So we'll go divide by 2. So again, this is the power, the value of me hearing, seeing how you are thinking about the problem. All right. That's really so important. And again, I will keep emphasizing it tonight. I really don't care if you get the answer right or wrong, but seeing how you think about it is going to help me help you. And if you're an educator, the same is true. So that's one of the tools when we're doing computational thinking. I need to understand how you are thinking about it so I can work with you. So I'm not interested in exams. Let's have a look at how I would think about this problem. Now, if we go back to our original outline about some of the aspects of computational thinking, one of those categories was decomposition. So maybe with 26 people, the problem is too hard, feels a bit challenging, a bit unclear in our heads. Maybe that's why, apart from shyness, that you aren't putting your ideas out there. So let me go. Let me go to the workbench. So Prathana, can you just mute your microphone, please, if that's not an active contribution? So what we'll do, I'll get rid of this for this Tower of Brahma for the moment. So let's do what we described as some of the methods, some of the techniques for computational thinking. So maybe 26 is too big a number. Maybe we could do it this way. We could grow the problem. So we could start small and grow the problem and see what we see. So if I've just got one person and the same task, we know that one person doesn't need to shake any hands. 0. If we've got 2 people and we need everyone to shake hands, then it's just those 2 shake hands. So that's only 1 handshake. So with one person, 0 handshakes. With 2 people, 1 handshake. 3 people, how many handshakes are needed? They have to shake hands, 1. They have to shake hands, 2. They have to shake hands, 3. Have we got everyone? They've shaken 2. They've shaken 2. Both of these have shaken hands with that. So 1, 2, 3. So 1, they've shaken, just that 1. So we just need 3 for that. What do we get with 4? Some of you have a look at 4. Tell me how many handshakes do you need when you've got 4 people? 6. We're thinking 6. So this number is small enough that we would describe it, we can brute force it. We can check using common sense. We can check all of the options reasonably safely. But when I give you 26, you can't. So we go, all right, there, that's 1, 2, 3. They've shaken hands. This one, 3, so 3, 4, 5, 6. So whoever it was that said 6, I think you're right. We've got 6. Are we beginning to see a pattern? If we wanted to, we could then go, all right, what's the situation with 5? How many do we need with 5? So that's a way of decomposing the problem, kind of understanding how the numbers grow, the number of handshakes grow as the number of people grow. We can apply our pattern recognition. Can I see a pattern? Is there a mathematical pattern here? Maybe if I did the 5, I would get a number that would give me an idea. There's another way. And this is the beauty of kind of, computational thinking. There are many different ways to tackle these problems. And it's not right, wrong. It's just some of us have skills or interest in sort of thinking in different ways. So let me just put, a circle here to represent all of our friends. And I might choose, just for a convenient number, 12. So these dots here, Is everyone turning up on the video? Yep. So I might put in 12 dots representing 12 people. So I'd ask you the question, 12 people need to shake hands with each other once and only once. What's the number? 12 already feels like it's too large a number to do it this way, but let's try it this way. So let's start drawing in the handshakes. So 1, 2, 3, 4, 5, 6, 8, 9, 10, 11. That feels okay. Nothing surprising there. 12 people, one person shakes hand with 11. That's good. Let's go to the second person. They've already shaken hands with this first person. So the first person shook 11. The second person doesn't have to do that. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They need to do 10. Third person's already shaken hands with these two, or they've shaken hands with this person. I bet you can already guess how many hands this person needs to shake. I bet you're already there. But let's check it out. They've already shaken that. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. And I think you're pretty convinced now what the number of handshakes that this person will need to finish is 8, 7, 6, 5, 4, 3, 2, 1. And so the total number of handshakes is that. And so we could look at this, and if we wanted to simplify the maths even more, that's 12, that's 12, that's 12, that's 12, that's 12, plus 6. So we could do the multiplication and work it out. So if we've got 26 people to shake hands, then while the arithmetic might take you a little time, the total number of handshakes is going to be 25 plus 24 plus 23 plus 22 plus 21, and so on, down to 0. And now what we've done in this is also something very special. We've done decomposition. So we've started with the 26 problems, too complex, I'm lost. Let's make it small and grow it up. Here, we've in fact visualized it. We've made a map of the problem, and looking at it, we use a different part of the brain to think about the problem. And really quickly, we saw the pattern. So if we take these ideas and turn them into patterns, turn these problems into patterns, we can think about these things very quickly. And we are very powerful at solving those sorts of visual problems, those visual relationships. So that's kind of decomposition, pattern recognition. You could now, if you wanted, write an algorithm, write the equation, the formula, write the software to go and calculate that. Drawing this is an activity that I get very young children to do. So we get a pie plate, some cardboard and some pins or pens and string, and we go and make the patterns. And I get the students to go and count how the numbers of strings change as you start joining up all the different dots. And even though they're not knowingly solving this problem, they're seeing these patterns emerge. And that's very powerful learning for them. Later on in school, in life, if they get into these combinatorial problems, they've got some common sense, some gut feel for about how you might tackle those problems. So that's about handshakes. Is that just a cute maths problem? Are handshakes important? Is understanding that mathematics? Do we see that mathematics is relevant or valuable? Is that something which, can any of you think where handshakes is important in daily life? Meeting friends, but anywhere else? Where is the idea of handshaking likely to be important, do you think? So we've got people coming together, connections. In human biological terms, it's really important. What about in technical terms? What other kinds of handshakes? What other kind of handshakes are there? We've got someone who's made a suggestion in kind of negotiation. There's a great area of computational thinking about negotiation. Really, really important mathematics. This is not linked so closely to negotiation, but that's another great topic to work on. How many people, I want to see some answers to this question. How many people today used a mobile phone? Quickly just put yes in the chat window. Who's used a mobile phone today? It's a really simple question. You're probably not going to get a simpler question tonight. Just 2 people have used, 3 people. How many people have used a mobile phone? If you haven't, let me know. All right. My assumption is pretty much everyone of you has used a mobile phone today. Every time you turn on your mobile phone, it has to connect to the network. That connection to the network is a handshake. Your phone has got its SIM card and its recognition, and you want to make a call or check a website. That's got to shake hands with the tower to go, I'm on your network. I'm a phone and I want to get on your network. That's one handshake. There's another handshake is going, well, what number are you? Oh, here's my number. Have you got credit on this network? I better go and check with the server to check your account to see if you've got credit. And that's a different handshake. And that server may check with a different bank and go, yes, they've got credit. And so even before you're allowed to make the call on your network, there may have been 4, 5, 6, 80 handshakes. And there's over 1 billion people in India, as you know. And they're all using or wanting to use mobile phones. So if you don't understand how the mathematics of handshakes changes as you go from 6 people to 26 people to 1 billion people, if you don't understand the number of handshakes, even that something as simple as that, if you don't understand how the number of handshakes changes, you don't know how to build your network, your communications network, because you don't know how much traffic, how much handshaking it's got to support. And so kind of every interaction, every digital interaction that you have in your life, every time you go to a web page, that's thousands of handshakes to secure the connection, to make sure that the right page is sent to you through 10 or 100 different exchange points to get to your screen. And so this might look like a party game, but understanding the mathematics of handshakes is about networks. And our lives are totally based on networks, personal networks, but technical and digital networks as well. So hopefully that's kind of given you some different thoughts about how you might challenge students to think about a problem, how you might get them to break it down and get a different understanding, how you might get them to visualize it. You know, sometimes just keeping all the moving parts clear in our heads, too hard for me anyway. But if we can come up with a way to visualize it, then we can use a different part of the brain and we can see different solutions. often very quickly. So that's handshakes. That's handshakes. What I might do now is hopefully kind of reinforce that point about thinking about a problem in a different way. So deconstruct it, visualize it in a different way, can make the problem feel very different. So let's go back to the board, and I'm going to give you a different challenge to think about. So there's our handshake. Let's get rid of the handshake for the moment. And what I'm going to give you is a challenge, a puzzle, a game that I would like you to try and solve. And it's based on chess, which is a game that I know is very popular in India, and the standard modern version of chess owes a lot to the versions of chess that were developed and have been played in India for a very long time. If we just get the camera to focus. Thank you. The game of chess that I'm going to get you to play is a little different to the normal. If I was sort of, after some jokes, I would suggest this is how we play chess in Australia, but that's not true. So rather than a chessboard, imagine that we've got this grid, and I'll number them in this way: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the chess piece that we're going to be using tonight in some countries would be called the knight or the horse. So that's my picture of a knight, a chess piece called the knight. And the knight moves in sort of the most unusual way of all the pieces on the chessboard. It kind of can move in an L shape. The L is kind of in a 2 by 1. And it really doesn't go through these intermediate squares. It kind of teleports, jumps from here to there, or it could go from here to there, or from here to there, etc. So the knight moves in that fashion. Hopefully most of you are familiar with that. Some of you might be very familiar with the moves. The challenge that I'm going to set for you now is I want you to take your knight and start on square 1. And I want you to find the path, find the sequence of moves that can get you from square 1. So the knight lands on every square once and only once, and on its last move can get back to square 1. All right. So it has to visit every square once, only once, and on the last move it needs to get back to square 1. So it's going to go on a tour of all of these squares. So if it starts on square 1, the first squares it could go to 2 and 1. So it could go to 7, could go to 2 and 1 this way, could go to 9, could go to 6. So on its first move, it could go to that 3, one of those 3. Can't go to 3, can't go to 12. Those are the only ones. And from there, it can choose where next to go. So I'll give you a few minutes to try and solve that problem. It's called a knight's tour. Start on square 1. As you're trying to solve it, do keep track of the moves. So you go 1 to 7, 7 to 5, maybe. Keep track of the moves, because when you say you have solved it, I'm going to ask you for those those moves, those numbers. So if you don't understand the challenge, just let me know, pop a message in, and we'll see how you go. I'll give you 5 minutes. The shortest time I've ever had for someone to answer this problem was probably a young 10-year-old boy in Calcutta. He took 15 seconds, might have been less. Very impressive, slightly scary. I'm not that fast. So explore the board, find the moves that can get the knight from square one to land on every other square once, but still get back to square one on the last move. See how you go. If you're not clear on the rules, just let me know. You cannot go from 1 to 3 in the first move because it needs to go 2 and 1 or 1 and 2. So on the first move, it can go from square 1 to 7. It can go from 1 to 9, and it can go from 1 to 6. 1 to 4, no, can't go from 1 to 4. So the only options for the first move are from square 1 to 7, from 1 to 9, or from 1 to 6. They're the only ones which fit that kind of L-shaped move. So it can have any of those shapes. Have any of those shapes to it, but has to be 2 and 1, 1 and 2 in that order. And if it goes from square 1 to 7, it doesn't mean that it's landed on 4 and 8. As I said, it's like Doctor Who, it tends to teleport. So it literally jumps from 1 to 7. So on a chess is on 4 and 8, that wouldn't stop the knight moving from 1 to 7. I'll give my participants another. I don't want you under pressure, so I'll give you another 240 seconds. See how you go. Some background music at this point, sort of waiting music. It would be a lot more fun for me if we were all physically together and I could see how you were working. Hopefully you're not trying to Google the answer. That defeats the point. So if I was trying to train you as a runner, Googling the answer is like you hopping in a moped and going to the finish line. Might get you there quickly, but it doesn't do anything to build up your strength. I'll give everyone a few more minutes. This is not easy, and that's okay. This is not easy. The next one I give you, I promise will be easier. So stick with it. You will get there. Anyone feel they're close? I expect if someone had what they thought was the right answer, they'd probably be sharing it. Hopefully the silence is because everyone is trying, but not getting there. I hope you're all trying. All right, we're going to time out on that problem. We'll come back to it in a little while. We're going to time out on that problem. I'm going to give you a different problem to work on. All right, I'm going to give you a different problem to work on. I'll take that one aside. And here I'm going to draw you a new shape. Right, so here's a new map. All right, so here's a new map, and I'm adding places of interest. They could be tourist destinations or hotels or buildings, doesn't really matter. So we've got these places of interest and we have these roads. And a little like the previous challenge, I want you to start here. And I want you to find a path, find a route that allows you to visit every dot, every place of interest, and come back to the start. You need to visit every dot once, only once, and end up being able to come back to the start. You don't have to use all the roads, but you do need to go through all of the points. So you're going to start here. You're going to go through every point once, only once, and end up back there. See how you go with that challenge. You can find a path. Done. Yashmina came back. What was that? 17 seconds. That was pretty good. Yashmina, can you share me the path that you chose? Can you describe that? If you want to unmute and just talk me through it.
From point 1,
Yep.
you can go inside.
So we went inside. Yep.
Yeah. Then go to then take a full circle.
Yep. Which direction? Clockwise or anti-clockwise?
Right.
Go right?
In clockwise direction.
Clockwise? Okay, so going clockwise in a circle. Yeah. Stop here.
Yeah,
Yep.
Then come outside.
Outside?
Yeah. Yeah, then anti-clockwise.
Then anti-clockwise. Perfect.
Yeah.
Perfect. Good job. Good job. Did that feel easier than the previous puzzle?
Yeah.
Otherwise, you're telling me you solved it, but you just didn't want to make everyone feel jealous. So you weren't sharing your previous solution.
No, I solved it, but I missed 2 points actually.
Okay, so you solved it, but you didn't solve it. All right. The other one's hard. The other one's hard. So your path that you gave us, Yasmina, there, in fact, that's 2 different solutions. That's 2 solutions. So you said, well, come in, go round, and come back. That's good. But it also means we could do the same loop backwards. So we could do this loop and end up there. So that's 2 solutions that we've found. Can anyone find another solution? Can anyone find another solution? Any other solutions to that? So Yashmina found what she thought was 1, but it's really 2, because we can do it in the reverse order.
Yeah, I found another one.
You found another one. Are you the only one working tonight, Yashmina? That's a joke. That's a joke. It sounds as if you're the only one working tonight. All right, what's your other solution?
Yeah, from 1, you have to go anti-clockwise. Anti-clockwise 3 points.
How far? Anti-clockwise?
1 point.
Yep.
Second point.
Yep. Where do I go next?
From outside, second point.
Yeah, second point is ambiguous. You mean do I go inside?
No, outside.
Outside, second point?
And then outside, third point.
Yep.
Then go inside.
Inside, yep.
Then again anti-clockwise.
Oh, anti-clockwise. You sure?
Sorry, it's clockwise.
That's better. Clockwise, I stop here,
Yeah, then go outside.
outside, and
Yeah, then come
back
to the
around
point
here.
one. Yeah.
That's great. That's great. So, and we could do the one you just suggested in the reverse order as well. All right. So that's another 2 options. And if we look at those, that suggestion you just came up with then is really kind of a mirror image of the first path that you found. So I'm sure some of the others of you have found those solutions as well, but Yashmina has found 4 solutions to that, which is great. Has anyone, Yashmina said she'd solve this except for 2, which is not really solving it, but she was having a good go. Has anyone solved this yet? Has anyone got 4 solutions to this yet? Or is this still very hard? Is it too hard? Is anyone still trying to solve this one? Or you've all given up? Which would be sad, because I'm trying to encourage you to be persistent. What I'll show you now is these 2 problems. In fact, see if I can get those. These 2 problems, in fact, aren't different. These 2 problems are exactly the same. These 2 problems are the same problem. They're just presented looking different, okay? And what you can do is you can take this problem. We'll get rid of this. So you can take this problem, which challenges you to think about all of the moves. This challenges you to think about all of the moves kind of in time. And so you've got to remember where you've been, think about where you haven't been, where you might be able to go next, and where that allows you to go after that. And that's what makes it hard. But what we can do is change that. So this problem I've presented you is kind of a challenge for you to think about in time. Step 1, step 2, step 3, step 4, in time. There's a sequence. But what we could do is we could look at the connections. And this is another really important technique for you to think about. So don't worry about the geometry of the board, because the geometry of the board is not important. What's important is which squares are connected by the knight, which squares are connected to each other. And it turns out, we're just going to put that over here. It turns out that if I draw all the connections, on this, they can look like this. Let's see if I'm right. So we start at square 1, and square 1 I can move, I'm connected to. I can get to 7, I can get to 9, and I can get to 6. So square 1 is connected to 3 places. All right, so those are 3 possible places it's connected to. Point 1 here is connected to 1, 2, 3 places. And that's kind of how we begin to draw this shape. So I can put, here we'll put 9 there. I'm going to put 6, because 1 is connected to 6. I'm going to put 6 on the inside. I'm going to put 7 over here. And if I do that again, 9 is connected to 1. It's also connected to 3. 7 is connected to 5 and 12. So I'll put 5 here, I'll put 12 there. So 7 is connected to 5 and 12 and back to 1. So it's got 3 connections, 1, 12, and 5. 5 is connected to 11 and back to 7. It's only connected to 11. 11 is connected to 10, 3, and 5. So 11 is connected to 3, 5, and 10. 10 is connected to 2. 10 is connected to 2, connected to 4, 2, and 2 is connected to 8 and 10. So I'm going to put 8 there. So that takes a little bit of working out to map the connection. So this is the task, this is the challenge. This is a map of the connections. So when we're working here, don't see this, we've got to remember all of those possibilities into the future and in the past. And our brains are not good at that. We're very visual creatures. So if I draw a map of the connections, I get this. And now, just as Yashmina did, we can look at the map and we can quickly see, oh, you can go in and around, back out and back this way. That's easy. All right, it's almost obvious, almost obvious. So let's see if that can give us a solution to this. So we're going to go in, around, out, and around. So that's going to go 1 to 6. So I'll cross them off as we go. 1 to 6. We're going to go around. 6 to 8. That's a legal move. 8 to 2. 2 to 10. 10 to 4. 4 to 12. We're going to go out. 12 to 7. 12 to 7. 7 to 5. 5 to 11. 11 to 3. 3 to 9. 9 to 1. And so we've now used this mapping. It's called building a graph. So this problem, really hard. If you had good coffee and a quiet room, beginning of the day, might take you 5, 10, 15 minutes to find a successful path for most of us. Here, most of us, even at the end of the day, can probably find that in under a minute. And some of us, like Yashmina, 10, 15 seconds, they can see a number of solutions. So this is 60 times faster, 60 times faster at solving these sorts of problems for us. And so we can begin to think about, if we were going to write a software program, we've got some ideas now. Don't worry about the geometry and just trying every possible move. That could quickly become very slow. But we can go and map all of the allowed moves and then just do the map and find the answer. Is that, what's people's thoughts about seeing something like that? For many of you, I'm assuming that's a kind of a very new approach to tackling some of those problems. You can't do that for every kind of problem, but there are some problems where that's a very good strategy. The bigger idea that is useful in lots and lots of situations is to stand back, abstract the problem. So the problem is not the geometry of the chessboard, the problem is the connections. Let me go and make the connections obvious. Now, how do I think about the problem? And that's part of computational thinking. Do you think that's an interesting activity? It's probably not one most of you have done. That useful, interesting, confusing? Do I need to explain some more about that? I find these sorts of approaches deeply rewarding to look at. And it is this idea, we will often, with our children, our friends, our students, if they're stuck, we will often tell them, try and think about the problem in a different way. And that's good advice. But what does thinking about something in a different way look like? So we're giving them good advice, but the student could easily go, what do you mean? Think about it in a different way. They don't have any models for how they can perhaps, visualize the problem, change it from a problem in time to a problem in space, make it spatial. We've got an enormous part of our brain that solves spatial problems like that. These kind of temporal problems of sequencing, we're not good. We're not good at it. Haven't been built that way. Let's have a look at another one of these sorts of challenges. Hopefully you're up for another puzzle, another challenge, and this also is going to give you an example of a different way to think about a problem. It's not going to be on the exams, but it is a useful thing to share with the students, I believe. So let's go back here. So this next challenge, this next puzzle to think about, hopefully it doesn't feel quite so difficult as the chess problem or the first version of the chess problem. Imagine now I have get some focus, please. There we go. Come on, my camera just likes to make up its own mind. So imagine we've got 3 jugs of different sizes. So let's imagine we've got our 3 jugs, and these jugs are solid. We can't look inside them. So we can't tell if they're kind of half full or 3/4 full. They don't have markings on them, none of that. So it's just a beautiful plain jug. And I'm going to tell you this jug can hold 8 liters of water, liquid. This can hold 5. This can hold 3. All right. So that's the jugs and their capacities. And what we start with is this jug is full. And what I want to get to, or what I want you to get to, is to end up with two serves, 2 portions of 4 liters each. All right, so this is 8 liters, 5 liters, 3 liters. you can't, for example, start pouring from the 8-litre jug into the 5 and guess where the 4 litres are, because you can't guess properly. The jugs are complex shapes. You can't see how full they are. You can't use a measuring stick to go in there because they're not simple cylinders. So the only thing you can do is you can pour until the jug you're pouring from is empty, or the jug you're pouring into is full. So that's the only times you can kind of stop. So I could take the 8 litres and start pouring into the 3. And when the 3-litre jug is full, I can stop. And I know it's got 3 litres, and I know this was 8 and I've lost 3. So at that point, I know there is 5 in here. I could check that by pouring it in here and it would be full, but I don't even need to do that. I know it's 8. I trust that number. I pour till this is full, 3. I know I've got 5 in here. So you can pour between the jugs as much as you like, but you have to pour until the jug is empty or the jug you're filling is full. But when you're done, I want to have 2 serves of 4 litres each, 2 portions of 4 litres each. I'll give you a few minutes to look at that. Again, try and record which jugs you were pouring into which jugs in which order, because we want to check and see how you got there. Give that a try. I'll give you a few minutes to explore that problem. If you've got any questions, just ask. See how you go. I like these sorts of problems. They get you thinking about your strategy. And as you'll see when we finish, they also give us examples of problems that we can solve in unexpected ways, which I also like. I'll give you a few minutes. I'll see how you folks are going. Perhaps I could have asked before I got you started, do you think it's possible? Or have I given you an impossible task? Do you think it's possible? Would I be that cruel? Do you think it's possible to get 2 serves of 4 litres from this arrangement? Your answer probably is more a sign of whether or not you trust me than the mathematics. You trust me to give you something that's possible. And thank you, Avipsa. Yes, it is. I thank you for your vote of trust. So yes, it is possible. Have you done it yet? Have you got there? Have you got an answer yet? See how you go. Avipsa, I will give you another 180 seconds. Maybe that feels more than 3 minutes. So Bikram, the task, the challenge is we have 3 jugs. One holds 8 litres, 5 litres, 3 litres. That's the capacity of the jugs. We start with the 8-litre jug full, and you can pour liquid from any of the jugs to the other jugs as many times as you like. But I want you to end up with 2 4-litre portions. And because these don't have graduations, they don't have volume markings on them, when you start pouring from a jug, you can either stop when the jug you're pouring from is empty or the jug you're filling is full. You can't kind of stop halfway because you don't know where halfway is. You don't have any measurement on those. So just using the known volumes of these. So as I said, I could pour from the 8-litre, start filling this one. And when this is full, I can stop and I'll know I've got 5 litres here and I had 8 minus 5 means I know I've got 3 in here. But I don't want 3 and 5, I want 2 serves of 4 litres. So hopefully that the task is clear. And if I was giving this task to some students in a classroom, I'd be asking them to talk about how they are thinking about the problem. What do they know? What do they think might help them with this? Because I want them to think about how they are thinking. And I want some of the students to hear how other students are thinking, not what the answer is. I want to make explicit, to make obvious and clear how people are thinking about the problems, because that's what they need to learn. They don't need to learn the answer, because tomorrow they'll have a different problem and it'll be a different answer. So what they need is to learn how to think about problems in a flexible way. So it's not just teaching them, oh, this is how you solve jug pouring problems. We want to actually try and teach them broader, more general strategies. So that's why we have that list of 4. Decompose, look for patterns, see what algorithms you can come up with. So, and these are things which you have not been trained as teachers to specifically help. So see how you go. I'm going to give you another minute. I'll give you another minute.
Hi, I think I got it. Can I say?
Yeah, sure. That's you, Vipsha?
Yeah.
Yep. Okay. What's your sequence?
First, can I say the first jug? Second, okay, I'll take the bigger jug. The biggest jug will be first poured to the 5th. I'm telling from the left, it's the first jug, second jug, and third jug.
Yep.
Yeah.
So you're going. You're going 1, 2, 3. Yep.
3. First 1 is poured into 2, so that will leave it with 3 liters, and the 5-liter jug is full now.
Yep.
Okay, and then 3, 2, 3. Yeah. Then the first is completely poured into the 1 minute. Yeah. Then the 5th jug is then poured to the second. The second jug is poured into the third.
So we're doing here to here?
Yeah.
All right. So that leaves us with 2 in here, and we've got 3 in here. Yep.
Yes. Then the 3 liters is poured into the biggest jug. That will make it 6 liters.
Okay, so we're going from here to there. So we
Yeah.
empty that. And this is now up to 6. Yep.
Yes. Then the second one, the 2 liters is poured into the third 3 liters jug.
So we've done that. Yep.
Yeah. Then the 6 liters is poured into the 5 liter jug. That will leave it with 1 liter. Yeah. Then 1 liters. Okay. Then the fifth one is okay, 512. I got confused in the one.
Can I give you help just for that last
Speak.
step?
Yeah, I think I got confused in that one.
Sir, in the
Are you-
previous step, it can be corrected.
So if we then pour from here into
5 to
here,
yeah.
then
Yes.
that
Then
will
it's
be 3 down 1. We've got 4.
yes. And
And
we'll
then-
again pour the third one into the first one. Yes.
Excellent. Well done, Avipsha. Good job. Applause, everyone. Okay, excellent. Excellent job. And this is, I like, I shouldn't say I love all of these problems, but I do. I think these are wonderful problems. And when you hear the students, if you ask the students to vocalize, to share how they're thinking about it, then this really helps them solve the problem, but it helps everyone, helps you understand how they're thinking. So the sorts of things you will hear is going, oh, the differences between these. So this can give me a difference of 2. 2 is interesting. 2 is interesting because if I can get 2s, I can get 4. Don't know where that takes me. This is the same difference, you know, and to hear them think out aloud how that's going is very useful. So as I said, not only is it the student that's doing it, but the students are hearing how other students think about it is more powerful than you trying to tell them how to think about it. All right, it's just one of those things. Let me share with you, you know, perhaps another different, a very different way of looking at this problem. Because if I gave you this problem and I said, I want a serve of 6 liters, 1 and 1 liter. So I've got 8. Can I get 6 1 and 1 liters serves? Is that possible? Now, if I set you that task now, it's really a whole new task. You solving the previous task doesn't really help you solve this task. It feels as hard or as challenging as it was a moment ago. And that question I asked you was, you know, before you start, is it possible? Is it possible? You trusted me, and thank you. But I have to say, I don't know if this is possible. I don't think this is possible. All right, I don't think that's possible. I don't think you can. Now, maybe I could leave you all night trying to do this. And if after 12 hours you hadn't solved it, would that prove that it's impossible or just that you haven't solved it yet? And this is another thing which we really need to know if we're tackling hard problems. You know, is there an answer? That's a very important thing to know before we start. So is it possible? Be great if I know that before I start. So let's look at a different way of viewing that. And we're going to make another graph of what's going on here. And not everything in computational thinking means you need to draw a graph, but it's a very powerful tool, and it's something which the students probably will never see if you don't show them, not unless they get into some of the areas within universities. So I'm going to draw a graph, sort of a table, but I'm going to draw a graph of our jug problem that we had before. And on this axis of the graph, we're going to have 0, 1, 2, 3. So this is a measure on this axis of how much is in our smallest jug, our 3-litre jug. Along here, I'm going to have a graph. This axis, the x-axis, is going to be a graph of what's in the middle jug, jug 2. All right. Let me just sort of frame that up. And so we might remember from the rules that I described to you that when you start filling a jug, you either stop when the jug is full or the jug you're pouring from is empty. All right. So this is our 3-litre jug. This is our 5-litre jug. We don't have to show our 8-litre jug. That's over here. This is our 8-litre jug. If the liquid isn't in our 3 or 5-litre jug, we know it's over here. All right, because that's the only other place it can be. So let's just think about what this graph might show us. So imagine I'm starting with, we fit it all in, the 8-litre jug is full, and I'm going to fill the 3-litre jug. So at the moment, the 5-litre jug and the 3-litre jug are empty. So that means the point, the data, is here. Both the 5 is empty and the 3 is empty. Do we see that? So I'm now going to fill up the 3-litre jug. So when I fill up the 3-litre jug, I start filling it up. I can't stop here because I don't have a 1 litre mark and there's more liquid in the 8 litres. Can't stop there. I can stop here when it's full. So I can move from here to there. I can't stop on the way. I can be here. So I can fill the 3-litre jug, and that lets me know what all the jugs have. This is 3, the 5-litre jug is 0, so there must be 5 back over here. I could pour the liquid from the 3-litre jug into the 5. So what would that look like, that transfer? So the 3 could be poured into the 5. So if a litre comes out of the 3, it'll be down here, but that means a litre will have gone into the 5-litre jug. So it can get to here. If I keep pouring, I'll have poured 2 litres into the 5-litre jug. That leaves 1 litre in the 3-litre jug, but I can't stop here because the 5-litre jug's not full or empty, and the 3-litre jug's not full or empty. So I can only stop when I get to here. So I've now poured all of the 3 litres from the 3-litre jug to the 5-litre jug. That's what this graph is showing me. So I can start here, fill up the 3, empty it to the 5-litre jug, and I've got 3 litres here. And the rest of this all makes sense. It's just I can't stop out here. So I can really only stop when I hit the edges. All right. So from here, I could fill up the 3-litre jug again from the 8-litre jug. So again, I can keep pouring from the 8 litres. I've got 3 litres in the 5-litre jug. So I know I've got 5 litres back here. So I've got enough to fill it. So I can fill it up again. And so I can be here. And then let me just draw a couple of light lines across here, just to sort of fill in the graph. So I can fill the 5 litre, I can fill the 3 litre jug up from here, get up to here. So I can be there, and that tells me I've got 3 litres in the 3 litre jug, 3 litres in the 5 litre jug. I've got 2 over here. I pour this into the 5 litre jug, and you see that all of these transfers are 45-degree lines. Every litre I put into this jug has to come out of the other. Three litre jug's got 1. I could pour all of the 5 litres back into the big tank. So I could end up over here. So I just emptied the 5 litres, put it into the 8 litre tank, and I'm back here. So the 3 litre jug's got 1. I could transfer that to here. I could then fill up the 3 litre jug, be here, and then I could transfer the contents of the 3 litre to the 5 litre jug. Oh, look, I've ended up here with a 4 litre serving. So in fact, what we discover is all of these pathways going up and down and around, all of these are possible transfers. All of these are possible positions. We would call them states. These are all possible states that the jugs can be in. All of these bits. And so we can go, if I want a 4 litre serve, I've got to get to here. And so we can see like a billiard ball bouncing around. That's one of the ways to get a 4 litre serve. So if I asked you, let's go back to that other question. With those jugs and those rules, can I get a portions of 6, 1, and 1? So if it's a 6, the 6 has to be in the big jug because 6 won't fit in the 5 or the 3. So that means, can I get 1 and 1 in the 5 litres and the 3 litres? So where is 1 and 1? 1 and 1 is out here. 1 in the 5, 1 in the 3. That tells me it's impossible with our rules, because our rules are you can only stop when one of the jugs is empty or one of the jugs is full. And out here, none of the jugs are full or empty. So we can't stop here. We can't get to that point. We can go through it, but we can't stop there. So this now, even though that takes a little bit of time to build it, I can quickly look at a challenge that you give me to go, no, it doesn't matter if I work for 1,000,000 years with those rules, I'll never get this answer. And so this is another way to visualize the process. And it gives us a very different way of thinking about the problem, a very different way to understand what's happening. Now, I'm not sure, I don't know you as teachers, so I don't know which subjects or grades that you're teaching. But I think some of these different ways of looking at a problem are very useful to introduce to students as early as you can, because it's not a question of will they get it right yet? It's a question of introducing the option to think this way or to think differently with any of these other tools. And that's useful to introduce to them as early as possible, just to let them know there are different ways of thinking about problems, about looking at data, or thinking about how you think into things. So hopefully that's given you some interesting interesting insights into what you might be able to do. Has anyone got any questions about that activity or the points I was mentioning? Any questions? There is, for me, sort of a question of, if you understand what we were doing there, that's one thing, that's good. There is a different skill, a different challenge perhaps, about thinking about how you come up with those different approaches. All right, so that's a different activity. How do you think about those? How do you think about making those transitions? But again, if you haven't even seen that it's possible, the students won't even begin to think that they can. Given the time, let's go and have a look at an activity which is can be very, very simple, good for the younger students, but also if the students are doing some software and programming, it's another activity which they can certainly undertake. So with this activity, try this for yourselves. We sort of haven't given you a list of materials to prepare, but hopefully some of you will do these activities afterwards. So this is about algorithms and automation, and it's also something about the students themselves. So the first thing to do with this activity is to take whichever alphabet you're familiar with, whichever alphabet is suitable for you and your students. It doesn't have to be the English alphabet, but I will do it in English. I can trust you. I can assure you neither my Bengali nor my Tamil is worth trying. So we're going to take the alphabet, and just for the first trial, I'm just going to make a grid over here, and I might make this grid sort of 5 by 5 and a bit, and I'm going to put the English alphabet into the grid, so A, B, C, D. So I'll fill up the grid, G, H. And just in case we're interested in Z, we'll include it down here. And now I'm just going to assign, I'm now going to assign a number to each column. So 1, 2, 3, 4, 5. And this is kind of step 1 in the activity. And the next thing to do is to encode, use this grid to create a number, a code number, which is really an instruction based on my name. You can do it for your name, that's no problem. So my name is spelt this way, U-A-R-T. So Stuart, and so the code number using this particular matrix, and there's nothing special about this, it's just one I've drawn. So the code number is S is 4, T is 5, U is 1, A is 1, R is 3, T is 5. So that becomes my code number. So in fact, we're going to use that code number as the instructions for an algorithm instructions for a program. All right. So, for example, if we were going to try a VIPSA, if we try to encode her name, VIPSA, hopefully I've spelled that right. So that's 1, 2, 4, 1, 4, 1. All right. Has no particular cosmic significance about what the numbers are, or none that I'm aware of. And the next step is to take that, and if you've got ideally a sheet of graph paper, just trying to make sure we're fitting as much of this in as possible, we're going to use use those numbers as the instructions for making a drawing. All right. So we use those instructions to make a drawing. We're going to start. I think the camera is in as close as I can get it, but we'll see it clearly in a little while. So I'm going to start here, kind of in the center. We'll see whether or not this is visible on the camera. And so I'm just going to take my code number 451135, and I'm going to use that as the instructions to draw lines on the graph paper. So first one is 4, so I'm going to go 4 in this direction. Sort of 1, 2, 3, 4. And then at the end of that line, I'm going to turn 90 degrees. So 90 degrees anti-clockwise. Why? I'm just choosing the rule. That's my program. That's my algorithm. You can choose a different one. You'll get a different pattern. So I go this direction 4, turn 90 degrees, go 5. So 1, 2, 3, 4, 5. Then I'm going to turn again. So at the end of every run, every line, I'm going to turn 90 degrees anti-clockwise. So it's not left, right, left, right. It's not up, down. It's imagine that I'm a turtle running along this line. I get to here and I turn to my left 90 degrees. So then I'm going to go 1 and turn 90 degrees and go 1, turn 90 degrees and go 3, and then turn and go 5. 2, 3, 4, 5. All right, so that's my name translated from my name to a number through an algorithm, some software. We just haven't got it in a computer, and it's made that pattern. What would happen now if I repeated that? All right, so I got to here, I turn left and go back and I start again. So I go 4, 3, 4, turn left, which now is going down, 5, 1, 2, 3, 4, 5, turn left and go 1, turn left and go 1, turn left and go 3, turn left and go 5. So there is a pattern which has been created from that algorithm, and the data I've given it has been my name processed through that grid. All right, through that grid. Let's, for the moment, we'll take a VIPSA's pattern. Hopefully that's sort of visible there. I think it's visible. And so her numbers: 1, turn left, 2, turn left, go 4, 2, 3, 4, turn, go 1, turn, go 4, sort of back over here, turn, go 1. So if I start again, I'll turn, go 1, turn, go 2, turn, go 4, turn, go 1, go 4, turn, go 1. I'm back to where I started. So both of our names after 2 loops have come back to where they've started. Now, is that true of everyone's name? Is that true of how you made the grid? What would happen to those patterns if you changed the grid? And this is a playful exercise, or it can be, hopefully it is. The students can go and take their names, come up with their own encoding system, and see what happens to the patterns. If they change the encoding system, the pattern from their name will change. If they've got a long name, they will get a more complicated pattern. So we can actually then look at, once the students have got kind of the algorithm, the rules clear, and are kind of drawing the right patterns, they understand the mechanism, then we can, as it were, move and bring the problem to some software. So what we'll look at now, and I think given the time, this is probably one of the last things we can look at, and we'll leave some time for questions. We can take that idea now that they understand it, and depending on what software languages they might have access to, they will be able to try to write software to automate the process. So in computational thinking, most of the hard work, most of the valuable work happens before you get to the computer. You've got to understand the problem. You've got to have taken it apart. You've got to think through, how does the algorithm work? What are the rules that I need to follow to get this to solve or to work properly? And then once you've got that understanding, then that's a good time to go to the computer and look at the software to try and write the software to make it happen. If you start with the software, you won't know how to solve the problem, because the software is just the language. It doesn't help you decide what to say in the language. So let me just set this up so I can screen share this for us. Okay, there we go. So one of the languages that I quite like using, again, depends on the age of the students, is this. It's Scratch. It's one of the original sort of block languages. And it kind of, if you're familiar with it, you know what this program can do. If you're not familiar with it, it's free, open source. You can run it on your phone. You can run it on even a slow computer. Doesn't have to be connected to the internet once you've installed the software. And it's actually quite a good learning language. And you can do a lot of things with it. This kind of yellow tower in the middle is in fact kind of the software that I've put together, which is really the algorithm, is the rules that we were using for the drawing program we had over here. And so if I click on this green flag up here, the software will then run. I'll just make that sort of full screen for you. And so the software is just asking the input for my name. So we'll give it Stuart. So I'm just putting that in down here. We'll hit go. And we can see it sort of following the rules which I gave it. All right, so let me just stop that. I think over here, there we go. I gave it a few too many loops. I was playing around with that earlier. So let's try that again. So Vipsa. And we could try something like computational thinking. That's a long word, long name. And we'll see what sort of pattern emerges from that. And once the students get to that point where they've now understood the rules, they've translated it to software, now they can actually do a lot more exploring. If you're going to do all of that activity, all of that drawing by hand on a sheet of graph paper, you probably wouldn't experiment very much. You might do your name, your friend's name, your last name, your nickname. You might do a few of those, but you really probably wouldn't explore it very much. Whereas once you've now automated it, then you can look at all sorts of interesting variations. For example, what would happen if I changed the rules? So for our previous example, when we got to the end of a line, we turned 90 degrees. What if I said, I've just changed a number down here, which is the number, how much do I turn? Just change that to 45 degrees. And so we'll see how that works. Again, I'll put in computational thinking. And now at the end of each line, it's not turning hard left, hard right. It's now turning 45 degrees. And we see a very different pattern. I don't know if it's nicer or more pleasing, but that's just one of the things to observe from it. I think it's ending up looking all right. So there we go, computational thinking, following that rule, but turning 45 degrees at the end. And so this is, a playful, as I said, a playful way to sort of bring students into thinking about each of those stages, or at least a number of the stages that are involved in thinking about making. If we can just ask someone at the Science Centre to mute the person with the microphone on the motorbike, that would be good. On there. So we can introduce these sorts of concepts of algorithms, of processes, of taking data, looking at patterns, making patterns, and that's also a great introduction to the beginnings of computational thinking, which is in reality a very, very broad topic, and so it can be challenging to think about where to introduce it within the school system, within the current curriculum. Given the timing of that, I might pause there and throw back to my colleagues at the Science Centre that if there's any sort of additional questions from the participants tonight. I tried not to rush through all the activities, but hopefully you've got a feel for some of the kinds of approaches about trying a problem, about thinking the abstraction of the problem, visualizing the problem in different ways, and ultimately how you can take your understanding, your algorithm, your algorithmic thinking, and then automate that, which is kind of the end goal for computational thinking, using the power of computers and big data. But you can't use a powerful computer and lots of data until you understand the process that you're going to use those tools to kind of operate on. So we'll give you as many minutes as you need. If you've got any questions about that, be happy to try and answer those. So while we're waiting, we'll look at what Himansu looks like.
Sir, could you write the open source software for this?
Sorry, ask again.
Could you write the name of the open source software for using this?
Sure. So let me just swap this over, everyone. So this particular software which I'm playing with at the moment is called Scratch, as in you have an itch and you want to scratch it. It's free and open source. There is an enormous community of educators that use it, and so there are many examples already made. It was put together by MIT, and there are probably a dozen versions using a similar interface for learning programming. So it's a very good language for kind of first time introduction to software development. There are extensions to it that allow you to take this and connect your software to what we call physical computing. So sensors, motors, robots, and the rest of those sorts of things. But if you don't have access to that, you can still do a lot of learning, either on a tablet, a phone, or a modest PC. But there's a lot of forums and communities out there to help you get started. It's pretty quick to learn the basics, but then the real computational thinking is then how you translate the activity, like we were doing with the graph paper. How do you translate that into Scratch? And practicing that thinking is actually really very valuable, more so than just learning the language, just picking up the particulars of the language.
Sir, may I ask one question?
Sure.
If we interpret this pattern, sir, then what do we learn from this?
So that's a great question. Whether or not you're after what's important, if you're asking, is this important? Does it signify something? It's not. The short answer is no. It doesn't in itself signify anything particular. The value of sharing this activity is in the kinds of questions you can ask the students. So why does my pattern look the way it does? Why is your pattern so different? Tonight we've seen all of the patterns. Tonight we've seen all of the patterns kind of come back to the start, but some people's names will be like the edge of a tablecloth. There'll be a pretty decoration, but it will go on and on and on to infinity. It won't fold back and come to the beginning. So why is that? And so one of the values of this is it's enjoyable. The students get to see their names. They get to understand the process of starting with data, encoding it, using an algorithm to take their encoded data and to do something with it. And so that's the big message. That's the main message. Beneath that, then there are those other questions.
I could understand from your explanation that this is quite funny for children.
Well, it's personal. So they're using their name. They will look at their pattern and their friend's pattern and go, what's different? Why are they different? And it's getting that questioning, which is very valuable. So once they see what's happening, they will of course play and change everything, and that's great. So they will learn to see how those changes impact on the patterns. So Avipsa, you've asked a really important question. How do our students find these variations? One of the things is for you to be aware of these different ways of presenting the information and for you to share that with the students. Not every problem that they face will have a really, if you like, a very beautiful or interesting visual version. It will depend on the problem. And that's one of the things to recognize, is that we're trying to prepare our students to deal with a very big range of problems. And so there isn't just one strategy. It's important for them to understand a number of different strategies. So do I make it visual? Is that going to help? Let me try. I've been doing visual ones tonight because they work reasonably well via Zoom. But there are other strategies to work with the students for them to think about. And those are the things like with the handshake. I'm confused when I ask the question about 26. Let's decompose it. Let's make a small version of the problem. How do I understand it when it's one person shaking their hands, two people, 3, 4? Okay, I see a pattern. I think I'm going to use the pattern to go and help me deal with the more complex situation. So these are just some general, these are general techniques. So, decomposing, working backwards, take a big problem, make it small and grow it. Take a big problem, shrink it, and see how your understanding of the problem changes. So because we don't know what specific problems the students will face, we need to give them general strategies. And that will prepare them much better than just giving them specific examples about how to solve a specific problem. So, if I give you, here is a quadratic equation, this is how you solve a quadratic equation, then they'll be able to do that. But if I give them a different kind of equation, they will be lost. And so it's this kind of teaching to one problem, one solution, whereas the computational thinking is going, these are bigger, less well-defined problems that you will encounter later in study, later in life. And you need to be a bit more flexible with how you're going to try and make sense of them. So if you're particularly interested in these sorts of techniques, everyone is more than welcome to get in touch with me. So I'm just putting my email address, sciencenomad @gmail.com. Or you can look for me on Facebook or Twitter, but Facebook. But if you're particularly interested in some more of this computational thinking type activities, send me an email and just let me know what sort of teaching you're doing, what ages, what subjects, and I will do what I can to send you some resources that you'll be able to try in your classrooms to go and get more of a feel for this. It's a very different way of teaching, and it's a new topic for you. And it's not easy, but I'd love to try and be of some help. So Avipsa and anyone, send me an email and I'll share with you some specific resources that you'll be able to use in the classroom.
I hope those who wanted to interact, they have shown their interest. And now I, on all behalf, beg your permission to close the session. And
Indeed.
Should we close now?
Yes, that's fine.
So now this is the end of the session. We had started on 28 and continuously we tried our best to come an end on this day. Sir, have you taken your dinner?
Indeed, I have.
Oh, nice. What time is that? Is it there in your place?
So it's 11 p.m.
Oh, so you want to go to bed now?
It's well, I will relax, but I've certainly had my dinner. Yes.
Yes, it was a pleasure for all of us. You know, with the support, as you said, it is a diplomatic relation. With the support of Consulate General of Australia in Kolkata, and with permission from Dr. Stewart, who visits all over the world, we got the chance to interact with each other and to be inspired. And then the journey never ends. I hope many schools will come forward to contact Dr. Stewart, to have an inspiration for your children. You know, this process will continue. As you know, there was a time when we started with Mr. Stewart, and then this time with E people, you are continuing. So also this process will continue further and further in geometric progression. I think pattern is geometric progression. And
I hope
a
so.
lot of thanks to all those involved, including Mr. Naeem, with support. Actually, he was to join this concluding session and address all, but unfortunately, because of some urgent work, he is not available. He has written a mail to us. So that is why we are now coming to the end. Thanking all participants. So hope we meet once again, Dr. Stewart. Good night.
Indeed. And all the best to you and all of the educators there. So the next time I'm in Calcutta, I will make sure that I head south, visit the center, perhaps on the way to Chennai. So we will make a tour of it.
Okay, sir. Nice to meet and enjoy the
All right.
program.
Okay. Stay safe, everyone.
Thank you, sir, so much. Thank you all participants. Now let us close the session and be busy in your own work.